CHAPTER5 THE Romance OFTHEMOON. An observer endued with an infinite range of vision, and placed in that unknown center around which the entire world revolves, might have beheld myriads of atoms filling all space, during the chaotic epoch of the universe. Little by little, as ages went on, a change took place. A general law of attraction manifested itself, to which the hitherto errant atoms became obedient. These atoms combined together chemically according to their affinities, formed themselves into molecules, and composed those nebulous masses with which the depths of the heavens are strewed. These masses became immediately endued with a rotary motion around their own central point. This center, formed of indefinite molecules, began to revolve around its own axis during its gradual condensation. Then, following the immutable laws of mechanics, in proportion as its bulk diminished by condensation, its rotary motion became accelerated, and these two effects continuing, the result was the formation of one principal star, the center of the nebulous mass. By attentively watching, the observer would then have perceived the other molecules of the mass, following the example of this central star, become likewise condensed by gradually accelerated rotation, and gravitating round it in the shape of innumerable stars. Thus was formed the nebula, of which astronomers have reckoned up nearly 5,000. Among these 5,000 nebulae, there is one which has received the name of the Milky Way, and which contains 18 millions of stars, each of which has become the center of a solar world. If the observer had then specially directed his attention to one of the more humble and less brilliant of these stellar bodies, a star of the fourth class, that which is arrogantly called the Sun, all the phenomena to which the formation of the universe is to be ascribed would have been successively fulfilled before his eyes. In fact, he would have perceived this Sun, as yet in the gaseous state, and composed of moving molecules, revolving round its axis in order to accomplish its work of concentration. This motion, faithful to the laws of mechanics, would have been accelerated with the diminution of its volume, and a moment would have arrived when the centrifugal force would have overpowered the centripetal, which causes the molecules all to tend toward the center. Another phenomenon would now have passed before the observer's eye, and the molecules situated on the plane of the equator, escaping like a stone from a sling of which the cord had suddenly snapped, would have formed around the Sun sundry concentric rings, resembling that of Saturn. In their turn, again, these rings of cosmical matter, excited by a rotary motion about the central mass, would have been broken up and decomposed into secondary nebulosities, that is to say, into planets. Similarly, he would have observed these planets throw off one or more rings each, which became the origin of the secondary bodies, which we call satellites. Thus, then, advancing from atom to molecule, from molecule to nebulous mass, from that to principal star, from star to sun, from sun to planet, and hence to satellite, we have the whole series of transformations undergone by the heavenly bodies during the first days of the world. Now, of those attendant bodies, which the Sun maintains in their elliptical orbits, by the great law of gravitation, some few in turn possess satellites. Uranus has 8, Saturn 8, Jupiter 4, Neptune possibly 3, and the Earth 1. This last, one of the least important of the entire solar system, we call the Moon. And it is she whom the daring genius of the Americans professed their intention of conquering. The Moon, by her comparative proximity, and the constantly varying appearances produced by her several phases, has always occupied a considerable share of the attention of the inhabitants of the earth. From the time of Thales of Miletus, in the 5th century BC down to that of Copernicus in the 15th and Tycho Brahe in the 16th century AD, observations have been from time to time carried on with more or less correctness. Until in the present day, the altitudes of the lunar mountains have been determined with exactitude. Galileo explained the phenomena of the lunar light produced during certain of her phases by the existence of mountains, to which he assigned a mean altitude of 27,000 feet. After him, Hbelius, an astronomer of Danzig, reduced the highest elevations to 15,000 feet. But the calculations of Riccioli brought them up again to 21,000 feet. At the close of the 18th century, Herschel, armed with a powerful telescope, considerably reduced the preceding measurements. He assigned a height of 11,400 feet to the maximum elevations and reduced the mean of the different altitudes to little more than 2,400 feet. But Herschel's calculations were in their turn corrected by the observations of Halley, Nasmyth, Bianchini, Gruithuisen, and others, but it was reserved for the labors of Barr and Medler. Finally, to solve the question, they succeeded in measuring 1,905 different elevations, of which 6 exceed 15,000 feet, and 22 exceed 14,400 feet, the highest summit of all towers to a height of 22,606 feet above the surface of the lunar disk. At the same period, the examination of the moon was completed. She appeared completely riddled with craters, and her essentially volcanic character was apparent at each observation. By the absence of refraction in the rays of the planets occulted by her, we conclude that she is absolutely devoid of an atmosphere. The absence of air entails the absence of water. It became, therefore, manifest that the Selenites, to support life under such conditions, must possess a special organization of their own, must differ remarkably from the inhabitants of the earth. At length, thanks to modern art, instruments of still higher perfection searched the moon without intermission, not leaving a single point of her surface unexplored, and notwithstanding that her diameter measures 2,150 miles, her surface equals the 1/15th part of that of our globe, and her bulk the 1/49th part of that of the terrestrial spheroid. One of her secrets was able to escape the eyes of the astronomers, and these skillful men of science carried to an even greater degree their prodigious observations. Thus they remarked that, during full moon, the disk appeared scored in certain parts with white lines, and, during the phases, with black. On prosecuting the study of these with still greater precision, they succeeded in obtaining an exact account of the nature of these lines. They were long and narrow furrows sunk between parallel ridges, bordering generally upon the edges of the craters. Their length varied between 10 and 100 miles, and their width was about 1,600 yards. Astronomers called them chasms, but they could not get any further. Whether these chasms were the dried-up beds of ancient rivers, or not, they were unable thoroughly to ascertain. The Americans, among others, hoped one day or other to determine this geological question. They also undertook to examine the true nature of that system of parallel ramparts, discovered on the moon's surface by Gruithuisen, a learned professor of Munich, who considered them to be a system of fortifications thrown up by the Selenitic engineers. These 2 points, yet obscure, as well as others, no doubt, could not be definitely settled, except by direct communication with the moon. Regarding the degree of intensity of its light, there was nothing more to learn on this point. It was known that it is 300,000 times weaker than that of the sun, and that its heat has no appreciable effect upon the thermometer. as to the phenomenon known as the azure light. It is explained naturally by the effect of the transmission of the solar rays from the Earth to the Moon, which give the appearance of completeness to the lunar disk, while it presents itself under the crescent form during its first and last phases. Such was the state of knowledge acquired regarding the Earth's satellite, which the Gun Club undertook to perfect in all its aspects: cosmographic, geological, political, and moral. Chapter 6. Permissive limits of ignorance and belief states. The immediate result of Barbicane's proposition was to place upon the orders of the day all the astronomical facts relative to the Queen of the Night. Everybody set to work to study assiduously. One would have thought that the moon had just appeared for the first time, and that no one had ever before caught a glimpse of her in the heavens. The papers revived all the old anecdotes in which the son of the wolves played a part. They recalled the influences which the ignorance of past ages ascribed to her. In short, all America was seized with Sullinomania, or had become moon mad. The scientific journals, for their part, dealt more especially with the questions which touched upon the enterprise of the Gun Club. The letter of the Observatory of Cambridge was published by them, and commented upon with unreserved approval. Until that time most people had been ignorant of the mode in which the distance which separates the moon from the earth is calculated. They took advantage of this fact to explain to them that this distance was obtained by measuring the parallax of the moon, the term parallax proving caviar to the general. They further explained that it meant the angle formed by the inclination of two straight lines, drawn from either extremity of the Earth's radius to the moon. On doubts being expressed as to the correctness of this method, they immediately proved that not only was the mean distance 234,347 miles, but that astronomers could not possibly be in error in their estimate by more than 70 miles either way. To those who were not familiar with the motions of the moon, they demonstrated that she possesses two distinct motions, the first being that of rotation upon her axis, the second being that of revolution round the Earth, accomplishing both together in an equal period of time, that is to say, in 27 1/3 days. The motion of rotation is that which produces day and night on the surface of the moon, save that there is only one day and one night in the lunar month, each lasting 354 1/3 hours. But, happily for her, the face turned toward the terrestrial globe is illuminated by it with an intensity equal to that of 14 moons. As to the other face, always invisible to us, it has of necessity 354 hours of absolute night, tempered only by that pale glimmer which falls upon it from the stars. Some well-intentioned, but rather obstinate persons could not at first comprehend how, if the moon displays invariably the same face to the earth during her revolution, she can describe one turn round herself. To such they answered, "Go into your dining room, and walk round the table in such a way as to always keep your face turned toward the center. By the time you will have achieved one complete round, you will have completed one turn around yourself, since your eye will have traversed successively every point of the room. Well, then, the room is the heavens, the table is the earth, and the moon is yourself," and they would go away delighted. So, then the moon displays invariably the same face to the earth. Nevertheless, to be quite exact, it is necessary to add that, in consequence of certain fluctuations of north and south and of west and east, termed her libration, she permits rather more than half, that is to say, 5/7, to be seen. As soon as the ignoramuses came to understand, as much as the director of the observatory himself knew, they began to worry themselves regarding her revolution round the Earth, whereupon 20 scientific reviews immediately came to the rescue. They pointed out to them that the firmament, with its infinitude of stars, may be considered as one vast dial plate upon which the moon travels, indicating the true time to all the inhabitants of the earth. That it is during this movement that the Queen of Night exhibits her different phases, that the moon is full when she is in opposition with the sun, that is when the three bodies are on the same straight line, the earth occupying the center, that she is new when she is in conjunction with the sun, that is, when she is between it and the earth, and, lastly, that she is in her first or last quarter, when she makes with the sun and the earth an angle of which she herself occupies the apex. Regarding the altitude which the moon attains above the horizon, the letter of the Cambridge Observatory had said all that was to be said in this respect. Everyone knew that this altitude varies according to the latitude of the observer, but the only zones of the globe in which the moon passes the zenith, that is, the point directly over the head of the spectator, are of necessity comprised between the 28th parallels and the equator. Hence the importance of the advice to try the experiment upon some point of that part of the globe, in order that the projectile might be discharged perpendicularly, and so the soonest escape the action of gravitation. This was an essential condition to the success of the enterprise, and continued actively to engage the public attention. Regarding the path described by the moon in her revolution round the earth, the Cambridge Observatory had demonstrated that this path is a ray-entering curve, not a perfect circle, but an ellipse, of which the earth occupies one of the foci. It was also well understood that it is farthest removed from the earth during its apogee, and approaches most nearly to it at its perigee. Such was then the extent of knowledge possessed by every American on the subject, and of which no one could decently profess ignorance. Still, while these principles were being rapidly disseminated, many errors and illusory fears proved less easy to eradicate. For instance, some worthy persons maintained that the moon was an ancient comet which, in describing its elongated orbit round the sun, happened to pass near the earth, and became confined within her circle of attraction. These drawing-room astronomers professed to explain the charred aspect of the moon, a disaster, which they attributed to the intensity of the solar heat. Only on being reminded that comets have an atmosphere, and that the moon has little or none, they were fairly at a loss for a reply. Others again, belonging to the doubting class, expressed certain fears as to the position of the moon. They had heard it said that, according to observations made in the time of the caliphs, her revolution had become accelerated in a certain degree. Hence they concluded, logically enough, that an acceleration of motion ought to be accompanied by a corresponding diminution in the distance separating the two bodies, and that, supposing the double effect to be continued to infinity, the moon would end by one day falling into the earth. However, they became reassured as to the fate of future generations on being apprised that, according to the calculations of Laplace, this acceleration of motion is confined within very restricted limits, and that a proportional diminution of speed will be certain to succeed it. So, then, the stability of the solar system would not be deranged in ages to come. There remains but the third class, the superstitious. These worthies were not content merely to rest in ignorance. They must know all about things which had no existence whatever, and as to the moon, they had long known all about her. One set regarded her disk as a polished mirror, by means of which people could see each other from different points of the earth, and interchange their thoughts. Another set pretended that out of 1,000 new moons that had been observed, 950 had been attended with remarkable disturbances, such as cataclysms, revolutions, earthquakes, the deluge, etc. Then they believed in some mysterious influence exercised by her over human destinies, that every Selenite was attached to some inhabitant of the earth by a tie of sympathy. They maintained that the entire vital system is subject to her control, etc., but in time, the majority renounced these vulgar errors and espoused the true side of the question. As for the Yankees, they had no other ambition than to take possession of this new continent of the sky and to plant upon the summit of its highest elevation the star-spangled banner of the United States of America. CHAPTER 7 THEHYMNOF Canon BALL. The Observatory of Cambridge, in its memorable letter, had treated the question from a purely astronomical point of view. The mechanical part still remained. President Barbicane had, without loss of time, nominated a working committee of the Gun Club. The duty of this committee was to resolve the three grand questions of the cannon, the projectile, and the powder. It was composed of 4 members of great technical knowledge: Barbicane with a casting vote in case of equality, General Morgan, Major Elphinstone, and J.T. Maston, to whom were confided the functions of secretary. On the 8th of October the committee met at the house of President Barbicane, 3 Republican Street. The meeting was opened by the President himself. "Gentlemen," said he, "we have to resolve one of the most important problems in the whole of the noble science of gunnery. It might appear, perhaps, the most logical course to devote our first meeting to the discussion of the engine to be employed. Nevertheless, after mature consideration, it has appeared to me that the question of the projectile must take precedence of that of the cannon, and that the dimensions of the latter must necessarily depend on those of the former." "Suffer me to say a word," here broke in J.T. Maston. "Permission having been granted, gentlemen," said he with an inspired accent, "our President is right in placing the question of the projectile above all others. The ball we are about to discharge at the moon is our ambassador to her, and I wish to consider it from a moral point of view. The cannonball, gentlemen, to my mind, is the most magnificent manifestation of human power. If Providence has created the stars and the planets, man has called the cannonball into existence. Let Providence claim the swiftness of electricity and of light, of the stars, the comets, and the planets, of wind and sound, who claim to have invented the swiftness of the cannonball, 100 times superior to that of the swiftest horses or railway train. How glorious will be the moment when, infinitely exceeding all hitherto attained velocities, we shall launch our new projectile with the rapidity of 7 miles a second. Shall it not, gentlemen, shall it not be received up there with the honors due to a terrestrial ambassador?" Overcome with emotion, the orator sat down and applied himself to a huge plate of sandwiches before him. "And now," said Barbicane, "let us quit the domain of poetry and come direct to the question." "By all means," replied the members, each with his mouth full of sandwich. "The problem before us," continued the President, "is how to communicate to a projectile a velocity of 12,000 yards per second. Let us at present examine the velocities hitherto attained. General Morgan will be able to enlighten us on this point." "And the more easily," replied the General, "that during the war one was a member of the Committee of Experiments. I may say, then, that the 100-pounder Dahlgrens which carried a distance of 5,000 yards. Impressed upon their projectile, an initial velocity of 500 yards, a second, the Rodman Columbiad threw a shot weighing half a ton a distance of 6 miles, with a velocity of 800 yards per second, a result which Armstrong and Palliser have never obtained in England. This, replied Barbicane, is, I believe, the maximum velocity ever attained. It is so, replied the general. Ah, groaned J.T. Maston, if my mortar had not burst. Yes, quietly replied Barbicane, but it did burst. We must take then, for our starting point, this velocity of 800 yards. We must increase it 20-fold, now, reserving for another discussion the means of producing this velocity. I will call your attention to the dimensions, which it will be proper to assign to the shot. You understand that we have nothing to do here with projectiles, weighing at most but half a ton. Why not? Demanded the Major. Because the shot, quickly replied J.T. Maston, must be big enough to attract the attention of the inhabitants of the moon, if there are any. Yes, replied Barbicane, and for another reason more important still. What mean you? Asked the Major. I mean that it is not enough to discharge a projectile, and then take no further notice of it. We must follow it throughout its course up to the moment when it shall reach its goal. What? Shouted the general, and the Major in great surprise. Undoubtedly, replied Barbicane composedly, or our experiment would produce no result. But then, replied the Major, you will have to give this projectile enormous dimensions. No, be so good as to listen. You know that optical instruments have acquired great perfection. With certain instruments, we have succeeded in obtaining enlargements of 6,000 times, and reducing the moon to within 40 miles distance. Now, at this distance, any object 60 feet square would be perfectly visible. If, then, the penetrative power of telescopes has not been further increased, it is because that power detracts from their light. And the moon, which is but a reflecting mirror, does not give back sufficient light to enable us to perceive objects of lesser magnitude. Well, then, what do you propose to do? Asked the general. Would you give your projectile a diameter of 60 feet? Not so. Do you intend, then, to increase the luminous power of the moon? Exactly so. If I can succeed in diminishing the density of the atmosphere through which the moon's light has to travel, I shall have rendered her light more intense. To effect that object, it will be enough to establish a telescope on some elevated mountain. That is what we will do. I give it up, answered the Major. You have such a way of simplifying things, and what enlargement do you expect to obtain in this way? One of 48,000 times, which should bring the moon within an apparent distance of 5 miles. And, in order to be visible, objects need not have a diameter of more than 9 feet. So, then, cried J.T. Maston, our projectile need not be more than 9 feet in diameter. Let me observe, however, interrupted Major Elphinstone, this will involve a weight such as... My dear Major, replied Barbicane, Before discussing its weight, permit me to enumerate some of the marvels which our ancestors have achieved in this respect. I don't mean to pretend that the science of gunnery has not advanced, but it is as well to bear in mind that during the Middle Ages they obtained results more surprising, I will venture to say, than ours. For instance, during the siege of Constantinople by Muhammad II in 1453, stone shot of 1,900 pounds weight were employed at Malta. In the time of the Knights, there was a gun of the fortress of St. Elmo, which threw a projectile weighing 2,500 pounds, and, now, what is the extent of what we have seen ourselves? Armstrong guns discharging shot of 500 pounds, and the Rodman guns projectiles of half a ton. It seems, then, that if projectiles have gained in range, they have lost far more in weight. Now, if we turn our efforts in that direction, we ought to arrive, with the progress on science, at 10 times the weight of the shot of Muhammad II and the Knights of Malta. Clearly, replied the Major, but what metal do you calculate upon employing? Simply cast iron, said General Morgan. But, interrupted the Major, since the weight of a shot is proportionate to its volume, an iron ball of 9 feet in diameter would be of tremendous weight. Yes, if it were solid, not if it were hollow. Hollow, then it would be a shell. Yes, a shell, replied Barbicane. Decidedly it must be a solid shot of 108 inches, would weigh more than 200,000 pounds, a weight evidently far too great. Still, as we must reserve a certain stability for our projectile, I propose to give it a weight of 20,000 pounds. What, then, will be the thickness of the sides? Asked the Major. If we follow the usual proportion, replied Morgan, a diameter of 108 inches would require sides of 2 feet thickness, or less. That would be too much, replied Barbicane. For you will observe that the question is not that of a shot intended to pierce an iron plate. It will suffice to give its sides strong enough to resist the pressure of the gas. The problem, therefore, is this: what thickness ought a cast iron shell to have in order not to weigh more than 20,000 pounds? Our clever secretary will soon enlighten us upon this point. Nothing easier, replied the worthy secretary of the committee, and, rapidly tracing a few algebraical formulae upon paper, among which n2 and x2 frequently appeared, he presently said, "The sides will require a thickness of less than 2 inches. Will that be enough?" asked the Major doubtfully. "Clearly not," replied the President. "What is to be done, then?" said Elphinstone with a puzzled air. "Employ another metal instead of iron." "Copper," said Morgan. "No, that would be too heavy. I have better than that to offer." "What then?" asked the Major. "Aluminum," replied Barbicane. "Aluminum," cried his 3 colleagues in chorus. "Unquestionably, my friends, this valuable metal possesses the whiteness of silver, the indestructibility of gold, the tenacity of iron, the fusibility of copper, the lightness of glass. It is easily wrought, is very widely distributed, forming the base of most of the rocks, is 3 times lighter than iron, and seems to have been created for the express purpose of furnishing us with the material for our projectile." "But, my dear President," said the Major, "is not the cost price of aluminum extremely high?" "It was so at its first discovery, but it has fallen now to $9 a pound." "But still, $9 a pound," replied the Major, who was not willing readily to give in. "Even that is an enormous price." Undoubtedly, my dear Major, but not beyond our reach. What will the projectile weigh then? Asked Morgan. Here is the result of my calculations, replied Barbicane. A shot of 108 inches in diameter and 12 inches in thickness would weigh, in cast iron, 67,440 pounds. Cast in aluminum, its weight will be reduced to 19,250 pounds. Capital, cried the Major, but do you know that at $9 a pound this projectile will cost $173,050? $173,050. I know it quite well, but fear not, my friends. The money will not be wanting for our enterprise. I will answer for it. Now what say you to aluminum, gentlemen? Adopted, replied the three members of the committee. So ended the first meeting. The question of the projectile was definitely settled. Chapter 8. History OFTHE Canon. The resolutions passed at the last meeting produced a great effect out of doors. Timid people took fright at the idea of a shot weighing 20,000 pounds being launched into space. They asked what cannon could ever transmit a sufficient velocity to such a mighty mass. The minutes of the second meeting were destined triumphantly to answer such questions. The following evening, the discussion was renewed. My dear colleagues, said Barbicane, without further preamble, the subject now before us is the construction of the engine, its length, its composition, and its weight. It is probable that we shall end by giving it gigantic dimensions. But however great may be the difficulties in the way, our mechanical genius will readily surmount them. Be good enough, then, to give me your attention, and do not hesitate to make objections at the close. I have no fear of them. The problem before us is how to communicate an initial force of 12,000 yards per second to a shell of 108 inches in diameter, weighing 20,000 pounds. Now, when a projectile is launched into space, what happens to it? It is acted upon by three independent forces: the resistance of the air, the attraction of the earth, and the force of impulsion with which it is endowed. Let us examine these three forces. The resistance of the air is of little importance. The atmosphere of the earth does not exceed 40 miles. Now, with the given rapidity, the projectile will have traversed this in 5 seconds, and the period is too brief for the resistance of the medium to be regarded otherwise than as insignificant. Proceeding, then, to the attraction of the earth, that is, the weight of the shell, we know that this weight will diminish in the inverse ratio of the square of the distance. When a body left to itself falls to the surface of the earth, it falls 5 feet in the first second, and if the same body were removed 257,542 miles further off, in other words, to the distance of the moon, its fall would be reduced to about half a line in the first second. That is almost equivalent to a state of perfect rest. Our business, then, is to overcome progressively this action of gravitation. The mode of accomplishing, that is by the force of impulsion. There's the difficulty, broke in the Major. True, replied the President, but we will overcome that, for the force of impulsion will depend on the length of the engine and the powder employed, the latter being limited only by the resisting power of the former. Our business, then, today is with the dimensions of the cannon. Now, up to the present time, said Barbicane, our longest guns have not exceeded 25 feet in length. We shall therefore astonish the world by the dimensions. We shall be obliged to adopt. It must evidently be, then, a gun of great range, since the length of the piece will increase the detention of the gas accumulated behind the projectile, but there is no advantage in passing certain limits. Quite so, said the Major. What is the rule in such a case? Ordinarily, the length of a gun is 20 to 25 times the diameter of the shot, and its weight 235 to 240 times that of the shot. That is not enough, cried J.T. Maston impetuously. I agree with you, my good friend. And, in fact, following this proportion for a projectile 9 feet in diameter, weighing 30,000 pounds, the gun would only have a length of 225 feet and a weight of 7,200,000 pounds. Ridiculous, rejoined Maston. As well take a pistol. I think so too, replied Barbicane. That is why I propose to quadruple that length and to construct a gun of 900 feet. The general and the major offered some objections. Nevertheless, the proposition, actively supported by the secretary, was definitely adopted. But, said Elphinstone, what thickness must we give it? A thickness of 6 feet, replied Barbicane. You surely don't think of mounting a mass like that upon a carriage? Asked the Major. It would be a superb idea, though, said Maston. But impracticable, replied Barbicane. No, I think of sinking this engine in the earth alone, binding it with hoops of wrought iron, and finally surrounding it with a thick mass of masonry of stone and cement. The piece once cast, it must be bored with great precision, so as to preclude any possible windage, so there will be no loss whatever of gas. And all the expansive force of the powder will be employed in the propulsion. One simple question, said Elphinstone, is our gun to be rifled? No, certainly not, replied Barbicane. We require an enormous initial velocity, and you are well aware that a shot quits a rifled gun less rapidly than it does a smooth bore. True, rejoined the Major. The committee here adjourned for a few minutes to tea and sandwiches. On the discussion being renewed, gentlemen, said Barbicane, we must now take into consideration the metal to be employed. Our cannon must be possessed of great tenacity, great hardness, be infusible by heat, indissoluble and inoxidable by the corrosive action of acids. There is no doubt about that, replied the Major. And as we shall have to employ an immense quantity of metal, we shall not be at a loss for choice.